Okay, good morning. So we have been discussing about the thermodynamic characteristics of the moist air from the previous lecture. So in moist air, we have two important components: dry air and water vapor. Okay. So for particularly for dry air, what we have different gases, and the temperature currently whatever is the ambient temperature or required for air conditioning within the range of 0 to 50 degrees Celsius, that is significantly large relative to the critical temperature of the gases. So that's why we can easily apply the ideal gas assumptions. On the other hand, for water vapor, we found that the critical temperature is 374 degrees Celsius, and if this temperature is 374 degrees Celsius, then what will be happening? Our 0 to 50 degrees Celsius is very less in comparison to critical temperature. It means we do not have high temperature condition. So it means under certain conditions, if we simply follow the constant enthalpy lines in the superheated region, we found that at higher pressures, whenever we move from one pressure to other pressure, then enthalpy is becoming function of both pressure and temperature. On contrary, whenever we go to the low pressure conditions, then the enthalpy lines in the gaseous phase becomes almost horizontal, which reflects that the dependence of pressure on enthalpy is actually diminished, and enthalpy has become a sole function of temperature only. So we know that in a mixture of dry air and water vapor, if total pressure is P, then significant portion of dry air is available. So the contribution of pressure of the partial pressure or vapor pressure, so partial pressure whose maximum limit is vapor pressure. Okay, so contribution of vapor pressure is actually very small. How? Because we are going only up to 50 degrees Celsius. So at 50 degrees Celsius, if we check the corresponding saturation pressure, which will be becoming the vapor pressure, that is 0.08 bar. Okay, and below that pressure, whenever we observe the constant enthalpy lines on TS diagram, these are almost horizontal. It means on enthalpy, the sole dependence of temperature can be taken. So all of you agree to this point? So what I am saying that for water vapor also, enthalpy is a function of temperature, but water vapor is present in the gaseous phase. That's why my Hg is a function of temperature. I am writing in the gaseous phase. Is this point clear? Anyone is having any doubt about it?
374 degrees Celsius critical temperature पे होता है?
Yes, critical temperature where saturated liquid line and saturated vapor line joins together. Is this one clear? Okay. Now, one important point you have to understand. Whenever this vapor is present, water vapor is present in the gaseous phase, we know that it is in the gaseous state. Okay. So, water vapor in gaseous state can either exist in superheated state or it can exist in saturated vapor state. Is this point clear? All of you agree to this point? So, can you tell me, generally, when water vapor is present in the gaseous phase, then is it in superheated state or is it in the saturated vapor state? See, in this room I have moist air, okay, means it contains dry air and the water vapor. If I start cooling the air and immediately my dew formation starts, then I will be saying that water vapor was present in the saturated vapor state. But whenever I start cooling the air, if it takes some decrease in temperature initially and after some time dew formation starts, then I will be saying that it was initially in which state? Superheated state, and then we will be cooling. So now can you tell me under what conditions these two different states can exist? We have two things for water vapor. One is its partial pressure, other one is its vapor pressure. So what will happen when the partial pressure of water vapor is less than the vapor pressure of water vapor? One is this condition. Second condition is if Pw is equal to Pvw. Okay. So out of this and this, Which one will be superheated state? Which one will be saturated state? Second one will be corresponding to saturated vapor state. Okay. And first one will be corresponding to superheated state. You see, you are sitting in this room. So, can you tell me, is this room having saturated air? No, because saturated, if it is having saturated air, there will be lot of moisture content. Okay. So now, if I start cooling this room air, what will be initially happening? Initially, upon cooling, the temperature will be decreasing. Why do you come these days in classes? Every day I see 3-4 of you, you are just opening mobile phone in the class, entire class you are just focusing on that. Then why do you come? So if you are just coming for attendance, then don't come. So what I was saying, that if I start cooling this room air, so initially temperature will decrease. Okay, immediately phase change will not start. Okay. So basically, when partial pressure is less than vapor pressure, then it's a superheated state. But on the other hand, if I say that this room air is actually saturated, it means it contains maximum amount of vapor content which it can hold. Okay. So in that scenario, if I start cooling, immediately the vapor will start condensing, because whenever we decrease the temperature, then the moisture carrying capacity of that particular gas decreases. Okay, the moisture carrying capacity of the air will be decreasing. Why it will be decreasing? Because with decrease in pressure, the corresponding saturation pressure or vapor pressure will be decreasing. So in order to decrease the vapor pressure, some of the vapor molecules has to condense into the liquids. Is this point clear? So what it means that, if I represent water vapor on TS diagram, okay, and say this is my some constant pressure line. This is the constant pressure line, okay. And at this constant pressure line, if I am at this particular state A, okay. So in state A, my pressure is PW. Is this one clear? But the corresponding temperature TA, corresponding to TA, what will be saturation pressure? Say if state A, my temperature is TA. So this temperature is basically TA and PW is the pressure. Is this point clear? That is my state A. Now can you tell me what will be saturation pressure corresponding to TA? This is TA temperature. So any pressure line passing through this will be the saturation pressure line at TA. All are clear with this point or not? Because this horizontal line is representing TA. So any constant pressure line which is passing through the TA in the liquid vapor dome, that will be representing its saturation pressure. Now whenever we move in upward direction towards the critical point, then we know that pressure keeps on increasing. Pressure increases in this direction. What it means? It means that at TA temperature, PW pressure, which is the partial pressure of the vapor in moist air, it is less in comparison to saturation pressure at the same temperature. What it means? It simply means that it is not in saturated state. If it is not in saturated state, of course the pressure is less, it means it is in the superheated state. Is this point clear or not? Now, if your water vapor is at state A, if you start cooling at constant pressure, what will be happening? If you start cooling at constant pressure, initially temperature will decrease. Is this one clear? Temperature will decrease and pressure will remain constant because I am doing cooling at constant pressure. It will come up to this point, which will be saturated state. So now what has happened? The pressure remained same, but the temperature has decreased. Okay. So when temperature is decreasing, what it means? The moisture holding capacity of the gas is decreasing. With decrease in temperature, corresponding saturation pressure will decrease. If corresponding saturation pressure is decreasing, it means that air can hold less amount of vapor. Okay. So with decrease in temperature, the moisture carrying capacity is decreasing. So it means that I will be getting some temperature condition which is given as TD. Say this is my point D. I will be getting some temperature condition TD corresponding to which the PW pressure will become saturation pressure. Is this point here? So when PW is saturation at TD, so what I am saying now, PW is nothing but equal to Psat at temperature TD. When I have got this situation, it means for temperature TD, PW is now the vapor pressure. Okay, so it means I have reached to the saturated vapor state. Now after this point, if I start cooling, then what will happen? Immediately the moisture will start condensing and I will be having dew formation. So droplet formation. Is this point clear? So this particular point at which the formation of the liquid takes place, vapor to liquid transition takes place, this is called dew point. And the temperature corresponding to this condition is called as dew point temperature of moist air. Okay. Now you can relate this in a very simple way. For example, typically in summers, temperature is very high. Okay. So when in summers temperature is very high, air is having significant moisture carrying capacity. You do not see any dew formation. But in winters, temperature is low. So moisture carrying capacity decreases. So in winters, particularly in the morning, you find lot of dew formation because you are easily reaching to the saturated state even with the low vapor content. Okay, so when your temperature is high, then to reach to saturated state, more vapor content is needed. But when temperature is low, then saturated state can be achieved even with the low vapor content. Is this point clear? Anyone is having any doubt about this? So one interesting point, we have seen that when my partial pressure is less than the vapor pressure, then the state of water vapor in the moist air is nothing but the superheated state. And when the partial pressure is equal to vapor pressure, then state is saturated vapor state. Okay. So if I start cooling the saturated vapor state, immediately the moisture will start forming. However, if I am in the superheated state, first there will be sensible cooling of the mixture, moist air, and after it is reaching the saturated state, then only dew formation will start. Therefore, the temperature at which dew formation starts, that is called as dew point temperature. Is this one clear? We will once again come back to this particular diagram. But before that, let's now move our discussion again towards the enthalpy. So in terms of enthalpy, because moist air is containing dry air and the water vapor. For dry air, already in the previous lecture I told you that enthalpy will be sole function of temperature and considering reference state at 0 degree Celsius. It means at 0 degree Celsius, if I assume H is equal to 0 kilojoule per kg, then I can simply write HA as 1.005, which is the Cp value times T. Is this one clear? So for dry air, yesterday I have already written in the previous lecture. Now for water vapor also, the range of pressure in which we are operating, we found that enthalpy is again a sole function of temperature. But one interesting point, we found that whenever water vapor is present in the moist air, it will always be in the gaseous state. So if it is always be in the gaseous state, I must write here enthalpy of gas. All are clear with this point? Now, water vapor immediately does not come into gaseous state. In order to reach the gaseous state, it requires certain amount of energy. That's why whenever I have to define this HGT, first I have to consider the enthalpy of the water vapor in the liquid state. So, HFT. Okay, so what is enthalpy in the liquid state? Then liquid to vapor conversion will be requiring latent heat of vaporization. So it means HFG at T. Again a function of temperature. And then what I will be having? Some part of enthalpy, because it may so happen that if my moist air is not fully saturated, then the water vapor is in which state? Superheated state. So in superheated state also I will be having some sensible enthalpy portion. Okay, so that is H dash G, because Hg I am writing to total enthalpy, that's why I am using this as H dash G as T. Anyone is having any doubt about this? Okay, now like we set the we have specified the saturation reference state at 0 degree Celsius for dry air. Similarly we will be specifying the reference state for water also equal to enthalpy equal to 0 at T equal to 0. Okay, so corresponding to T equal to 0, I can simply write that liquid state enthalpy will be
टेम्परेचर 0 डिग्री होगा या केल्विन?
degree Celsius, because we are operating in 0 to 50 degree Celsius. Okay, all are clear with this point? So this reference state we are setting as per our convenience requirement for the moist air conditions. Okay. Is this point clear? So at 0 degree Celsius I can say that in liquid state HF is 0. All of you agree to this point? Now HFG at this condition is nearly close to 2500 kilojoule per kg. Okay, so within the range of 0 to 50 degree Celsius temperature, because this is a very narrow range of temperature, almost average value of latent heat of vaporization is almost 2500 kilojoule per kg. Is this point clear? And HG will be what? Hg will be enthalpy in the gaseous state. So I require Cp of the water vapor. So Cp of water vapor is close to 1.88 into temperature T. Is this point clear? Moreover, if one has to exactly calculate the value of enthalpy in the liquid state, then it must be written as 4.18. 4.18 kilojoule per kg Kelvin is the Cp of water in the liquid state. So 4.18 into T. All of you agree to this point? So if one is not considering the enthalpy at 0 degree Celsius, if we are at some temperature 25 degree Celsius, then for 25 degree Celsius the value of enthalpy in the liquid state must be equal to 4.18 into 25. Is this one clear? Because 0 we have set reference for 0 degree Celsius. Okay, considering presently, removing this part presently, I can simply say that my enthalpy of water in the gaseous phase can simply be written as 2500 plus 1.88 into T. Because presently I am considering liquid portion almost. Okay. However, if one has to do accurate estimation, then it has to be 4.18 into T. Agreeing to this point? So this is my enthalpy of water in kilojoule per kg. Now, what will be enthalpy of moist air? Enthalpy of moist air will be total mass of moist air into, generally enthalpy of moist air will be what? Content of water vapor into enthalpy of water vapor plus content of dry air into enthalpy of dry air. Is this one clear? So, however, so it means that if I have MW and MA as masses of water vapor and dry air, then the total mass of moist air will be MA plus MW. Is this one clear? Typically, the properties of moist air are specified in terms of per kilogram of the dry air. Okay, so usually if you see the total mass is MA plus MW. So usually if I have to define the specific property for the moist air, then specific property, for example enthalpy of moist air must be equal to capital H total enthalpy divided by mass of moist air. Okay, so this will be total H will be kilojoule, extensive property, per unit mass will be kilogram. Okay, but generally whenever we do study about air conditioning, we do not represent the properties of moist air in terms of its total mass. We represent the properties of moist air in terms of mass of the dry air. That's why I will be writing this kilojoule per kg of A, where kg A means dry. Is this point clear? You have to understand this point very, very carefully. Okay. So typically why this is done? Because whenever you are handling some specific amount of dry air, it can have different amount of water vapor corresponding to different temperature and pressure conditions. Is this point clear? For different temperature and pressure conditions, the amount of water vapor will be different in the given mass of dry air. So it means that this M mass in the air conditioning equipment will always be variable. It will be depending upon the amount of MW at any point of time within the air conditioning equipment. Okay. However, the mass of dry air which we are handling, that always remain constant. Is this point clear? So that is the reason that properties of moist air are even specified on per unit mass of the dry air. Is this one clear or not? This is important point because this M will be variable within the air conditioning equipment when humidification, dehumidification, etc. will take place. Okay, but the content of dry air which is handled by the equipment, that will always remain same. Considering this condition, I can simply define that MA is mass of dry air. So total enthalpy of dry air, total enthalpy of moist air, what it will be? If it is written in terms of kilojoule per kg of dry air, then total enthalpy I can simply write as MA into small h. Is this one clear? MA into small h will be equal to mass of dry air into enthalpy of dry air plus mass of water vapor into enthalpy of water vapor. Okay. So from here, if I write enthalpy on per unit mass of dry air basis, then MA will cancel, H will be HA plus MW by MA into HW. Okay. And ultimately, if I replace, then it will be 1.005 into T plus MW by MA into 2500 plus 1.88 into T. And this is nothing but kilojoule per kg of dry air. All of you are agreeing to this point? Okay. The way we define enthalpy we also define one more property. Okay, so this enthalpy can now be written as 1.005 plus 1.88 into mw by ma times of T plus mw by ma into 2500. Okay. Now, what does this portion represents? This portion is representing the latent heat of vaporization portion, phase change portion. Okay. And what does this portion represents? This portion is representing the sensible heat of dry air, first term, and second term is sensible heat of the water vapor present with the dry air. Okay. So it means that, and typically we know that the sensible enthalpy change is in the gaseous state is written in terms of Cp into T. Okay. So this entire quantity I can call as humid specific heat. Humid specific heat or specific heat of moist air at constant pressure. Is this one clear? Anyone is having any doubt about this? This is simply called as either humid specific heat or specific heat of the moist air at constant pressure. Okay, shall we move further? Yes. That's why this is air plus moisture, so it means humid or moist air. Okay. Now, now we will be defining one very important property which is called as specific humidity or humidity ratio. So there is one property while dealing with the moist air which is called as either specific humidity or humidity ratio. It is given by the symbol W and it is generally defined as the mass of water vapor per unit mass of dry air present in moist air at any temperature T. Okay. So mw by ma is something which is called as the humidity, but what are the conditions? mw by ma in a given volume of moist air at temperature T. Okay, so volume is given and temperature is T. Now let us, because for both water vapor and air I can apply the ideal gas equation. I know as per ideal gas equation PV can be written as M RT, where R is specific gas constant, because R can have two values, either it is universal gas constant or specific gas constant. So when I am writing this, then it is specific gas constant. If I am writing universal gas constant, then I will be writing PV into R bar by MT. What is R bar? Universal gas constant, and M is molecular mass. Capital M is molecular mass. Yes. So let me write for water vapor. Water vapor, say pressure is PW. What is volume? If you have moist air filled in this room, so water vapor will also be everywhere present. Okay, so volume will be same. That's why I emphasized earlier that volume and temperature are to be considered same. Okay, so volume is same. Now in the entire volume, everywhere water vapor is not present. So there will be some mass mw of water vapor. Okay, and R bar divided by molecular mass of water vapor into T. Now if moisture is contained in this room, dry air is also having same temperature, water vapor is also having same temperature. So T is same. Similarly, for dry air I can write PA into V MA R bar by MA into T. Okay. Make this substitution, replace MW and MA. What I will be getting? In place of MW, I will be getting PW into V, PW V into MW divided by R bar T, okay, and PA V MA divided by R bar T. R bar T will cancel, volume will cancel. So ultimately I will be getting, what I will be getting? MW by MA into PW by PA. What is MW? Molecular mass of water close to 18. Molecular mass of air is close to 28. I will be getting 0.622 into PW by PA. Typically, the total pressure of the mixture can be written as sum of pressure of water vapor plus dry air. From here, PA can be written as P minus PW. So, humidity will become 0.622 into PW divided by P minus PW. Okay. And the unit of this will be kilogram of water divided by kilogram of air, dry air. Is this one clear? So kg of water upon kg of dry air. So this important property is something which is called as specific humidity or humidity ratio. So generally we say this term very commonly that today humidity is very high. What it means? It means that the amount of water content in the water vapor content in the air is actually significant. Okay.
पर ये तो फिर यूनिटलेस ही हो गया ना?
Of course. Yes. Per kg, for per kg it is unitless. If you say 10 kg of dry air is there, then you will be having certain kg of the water. Okay. So now in the previous expression of enthalpy, what you can do, you can make this substitution. You can replace MW by MA with this W. So you will be simply just, you can make this replacement. Here this W will come, here W will come, and here also W will come. Okay? All are clear with this point? Now let's talk about next property, which is called as degree of saturation. So typically, if you have to test that how much your air is away from the saturated state, then this type of relative measures are used. There are two important quantities. One is degree of saturation and other is relative humidity. Okay. So have you seen any weather station screen or weather prediction? Whenever you see in your mobile phone, what it shows? RH 90%, RH 50%. Okay, so we get relative humidity from there. Okay, so the measures which explains the capability of the air to hold moisture with reference to the saturated condition, that is called as actually degree of saturation or relative humidity. Okay, so in terms of degree of saturation, it is defined as, typically given by a symbol mu, and it is defined as the ratio of specific humidity divided by specific humidity of the saturated air for given volume and temperature. Okay, because if you increase the volume, then of course content can increase. Okay, sorry, even volume is not needed for given temperature. because it always takes care of the volume in the humidity itself. Is this point clear? So degree of saturation is defined as nothing but the humidity of normal moist air divided by humidity of the saturated air. What do you mean by saturated air? When I will be calling air to be saturated. Saturated means when PW is equal to PWS. PVW or PWS, whatever you want to call. So let me call PWS. Okay. So if PW is less than PWS, then air is superheated. Water vapor is superheated. Okay. And moist air is unsaturated. But saturated moisture will be corresponding to PW equal to PWS. So I can simply define over here that WS will be 0.622 into PWS by P minus PWS, where PWS is nothing but equal to P sat at the given temperature for water vapor. Okay? Is this point clear? Now next is relative humidity. Relative humidity, many times it is simply called as RH, and it is also given by a symbol phi. Okay. So phi is defined as the ratio of mass of water vapor in unsaturated air divided by mass of water vapor in saturated air, MWS, for given volume of air and temperature. Here volume and temperature will come, because if you increase the volume, then automatically mass can increase. So within the same volume I have to make comparison. Is this point clear? So for a given volume and temperature, what is the mass of water vapor divided by mass of water vapor in the same volume and temperature for saturated air. So that is called as relative humidity. Okay. So relative humidity can further be simplified just from the previous equation. So if I do replacement with ideal gas equation, what I will be getting? MW I can replace as PWV into R bar divided by, into MW divided by R bar into T. This divided by PWS. Now saturated state. So PWS volume is V. Again I have water vapor only. So MW divided by R bar into T. So it will be simply becoming equal to PW by PWS. So the ratio of partial pressure of water vapor divided by saturated pressure of water vapor at the given temperature is something which is called as the relative humidity. All are clear with this point? Anyone is having any doubt? Okay, so we discussed about three things: specific humidity, degree of saturation, and relative humidity. I also introduced you one very important parameter which is called as dew point. Okay, and I told you that I will once again come back to that diagram. So let's see that diagram again. This was some PW pressure line. This was my state A. When I have done cooling under constant pressure, I reached to this point D, and this temperature TD was my dew point temperature. Usually whenever we deal with the moist air, we stop only up to this point. Okay, we don't go into the two-phase design. Why we don't go into the two-phase design? Because ultimately their liquid will be, vapor will be condensing into the liquid phase, and liquid droplet does not make homogeneous mixture with the water vapor. Liquid will be settling at the bottom because of its heavy weight. Okay, so ultimately our interest is only in the vapor phase. After this point, if you keep on doing cooling, that is not our interest, particularly for air conditioning applications. However, what generally happens, which we see also whenever we cool in our split AC or window AC unit, Then because of cooling, some moisture forms and that goes out. Okay. Another interesting point is, if whatever the given amount of mass of air I am having at point A for moist air, instead of cooling this under constant pressure condition, if I cool it adiabatically, what is the meaning of adiabatic cooling of moist air? How I can do adiabatic cooling? See, this moist air is in the superheated state, correct? All of you agree to this point? So, it is having tendency to capture more and more water vapor. If I use a big pool of water and I allow this air to flow over that pool of water, what will happen? And if I maintain that chamber which contains water and flow of air perfectly insulated, it means adiabatic chamber. From outside there is no heat. So what will be happening? If we have some water glass in this room and air is not saturated, you will be finding next morning you come, that glass will be evaporated. Okay. So if glass is evaporated and room is perfectly insulated, it means for water to evaporate it requires latent heat of vaporization. From where that latent heat of vaporization has come? From the surrounding air. So air will be losing energy in order to evaporate the water. Is this point clear? So it means that if I use a pool of water and over that if I allow air to flow, what that air will be doing? That will be evaporating some amount of water. And at max, if I say my pool is infinitely long, so it will keep on evaporating the water till the situation its temperature reaches to saturation condition. Okay, so maximum amount of water vapor it is having. So that type of process will be an adiabatic process where air from its own energy is actually getting saturated. So if I have to represent that process on TS diagram, that will be coming something like this. So what is this process? This process is of adiabatic cooling of air. Is this one clear? This is adiabatic cooling of air. With the adiabatic cooling of air, instead of point D, I reach to some saturated state, some point B. Okay. Now, the temperature of at point B is something which is called as adiabatic saturation temperature. What we call this? Adiabatic saturation temperature. And this is also called as wet bulb temperature. So if you simply do adiabatic cooling of air, then also it can reach to the saturated condition if you allow infinite amount of water cool. And corresponding to that, whenever it will be reaching to saturated condition, whatever the temperature we are getting, that is called as adiabatic saturation temperature or wet bulb temperature. And you usually will be experiencing that this wet bulb temperature will be slightly larger in comparison to dew point temperature. Okay. Now let's discuss this further. This is important topic, and it is having very practical utility. It helps a lot in defining the properties of the moist air. Adiabatic saturation temperature, or what I will be calling it as wet bulb temperature. Let's consider that I have one infinite long pool of water. So this contains water in the liquid state. Okay. and this pool is insulated. It is well insulated. And over this pool, I have a duct. This duct is also well insulated. Over this pool, I am allowing air to flow at some temperature T1, mass flow rate of m dot A, and humidity of W. Is this one clear? Now, whenever this air will be interacting with the water, what will be happening? The immediate adjoining layer of the air will be taking the water vapor which is evaporating from the pool, and in this immediate portion I will be having high concentration of vapor in comparison to remaining portion. Is this one clear? Because the air which is coming at the top portion, it is not interacting with the pool. So whatever vapor is coming from the pool, that will be having more concentration here, and here concentration will be less. Because of this concentration difference process, diffusion of vapor molecules will take place from this part to top part. Is this one clear? And this diffusion will keep on happening. Now if I have infinitely long pool, after certain time I will be finding, because initially here vapor is significant, here less. So diffusion will be fast. But when I will keep on moving, because here also some vapor has already diffused from this initial portion. So here also vapor concentration is continuously increasing. I will be getting a point in this portion as well as this portion. Vapor concentration cannot be more than the saturated condition. So when, because of the diffusion process in the long pipeline, here air is saturated, then I will be finding that concentration of vapor in entire section will become uniform. So there will not be any gradient. Is this one clear? All are agreeing to this point or not? And let's consider pool was initially at temperature T2. All are clear with this point or not? So, once the concentration has become uniform, it means my entire air is saturated. And in the process, while it is moving from inlet to outlet, it is not exchanging any heat with the surrounding. So, entire heat of evaporation is supplied by air only. So, there will be cooling of the air. So, because of cooling of the air, say it is coming at temperature T star. Of course, mass flow rate of dry air will remain the same under steady state condition, and humidity has become, say, Ws star. Ws is representing saturated state and star is representing corresponding to the temperature condition of adiabatic saturation limit. So this temperature is something which is called as adiabatic saturation temperature or wet bulb temperature. So the process A to B is basically happening inside this chamber. Is this one clear? So whatever process A to B I represented on the diagram, TS diagram, same process is happening over here. Anyone is having any doubt about this? Now one interesting fact you need to note down: if this air keeps on flowing, water level will keep on decreasing. It's a continuous flowing air. So in order to maintain the water level also at the same level, I need to supply some makeup water from outside. So with the help of a float, I can supply makeup water. So usually we should supply makeup water at T star temperature. Okay. I can supply this makeup water at some other temperature also. If I supply at other temperature, then also process will be happening, but the length of the pool required will be more. Okay. However, if I apply the makeup water at the same temperature as that of T star, then my length required will be decreasing. Is this one clear? Anyone is having any doubt? Now let us analyze this chamber. So if I take this chamber as my control volume, so what are the mass interactions? Please tell me. How much if I write mass balance of water? What is inlet mass of water here?
M.
M dot A, mass flow rate is M dot A into W1. That is the inlet flow of water. Outlet flow is M dot A into Ws star. In addition to that, from here also I am supplying some makeup water at the flow rate of M dot W. So plus M dot W equal to 0. So from here I will be getting that M dot W is nothing but equal to M dot A into Ws star minus W1. Okay. Now let me do the energy balance. If I do energy balance, then M dot A is coming with H1 enthalpy. M dot A is going with enthalpy HS star, and makeup water M dot W is coming with what enthalpy? Makeup water is coming in which state? Liquid state. So HF, and I told you generally we supply this at temperature T star. So this HF I will be supplying at temperature T star. So let me call it as HF star. Agreeing to this point? Any other energy interaction? Chamber is insulated equal to 0. So what I will be getting here? M dot A is common. H1. What is this H1? H1 is usually in the gaseous state. Hg. So let me write it as Hg minus Hs star. Okay. Plus Mw, which I can write as M dot A into Ws star minus W1 into HF star equal to 0. Okay. Anyone is having any doubt about this? Now, what I can write Hg? Please tell me. Hg can be written as 1.005 T plus W into 2500. Okay, let me write in generalized way. HFG plus 1.88 into T. Clear or not? Okay. So if I do this substitution and then if I rearrange, I will be finding that W is nothing but equal to Ws star into HFG star minus 1.005 T minus T star divided by Hg at T minus HF star, and of course what will be HFG star? Hg star minus HF star. Okay, so I have done some manipulations. How? You need to specify all these values in terms of HF and Hg, and after that we can do these manipulations. Okay, so this is something which is the equation for governing equation for adiabatic saturation chamber. Now let's see what are the, and this entire process was happening at which condition? Say everything was happening at pressure P, mixture pressure P. So this was my mixture pressure P. Now you see what is Ws star? It's a saturated state. For saturated state, I require only two properties for a mixture. If pure substance, then single, but for a mixture, two. One is pressure, which is fixed. Other will be nothing but T star. Okay. Then simply HFG star, again latent heat of vaporization, require two properties. One is pressure and other will be T star. What is W? Similarly, HF star will also be available at HF star at T star. What about W? W is not at saturated state. W is which state? Superheated state. So for superheated state, how many properties are required in moist mixture? Three properties. Pressure is there. Other will be temperature T, and third can be temperature T star. For that also there will be some wet bulb temperature. Okay. So it simply means that in this equation, if you see Ws star, HFG star and HF star, these are the values which are depending upon T star only. Okay. So it means from this equation you cannot eliminate and explicitly calculate the value of T star. You need to make some guess to T star. That guess, corresponding to that guess, you need to calculate all these values. All are clear to this point or not? And then you need to again iterate on this equation in order to come to a value of T star which is satisfying this particular relation. Is this point clear? So it means that this particular equation is nothing but an implicit equation, where whatever is the unknown, that itself is creating functional relationship for some other parameters. Okay. So that's why it's an implicit equation for T star. If you have to solve this equation, what you need to do? You need to do iterative method. Guess some value of T star, corresponding to that calculate all these parameters, substitute, check if equation is being satisfied. If it is deviating, accordingly either move in positive direction or negative direction depending upon the residual. Okay. And this way we can iteratively solve this. So it means that estimation of wet bulb temperature from the theoretical perspective is very, very challenging. Okay. But we have very easy estimation of this. Maybe I'll discuss in the next class. Let's stop here.